All right, welcome to another deep dive with us. This time, we're tackling something that, honestly, when you first suggested it, sounded a little intimidating. The emergence of first-order logic. I mean, logic can seem pretty abstract, even for a show like ours where we like to get into the nitty-gritty.
It's true. Logic does have that reputation. But I think what we'll find as we go through this is a really compelling story. Like, how do we get from, the ancient Greeks thinking about syllogisms
Yeah.
to what's now this foundation for so much of modern mathematics?
Right, and you've dug up this treasure trove of sources for us going way back. So our mission, I guess, is to kind of sift through that and see if we can pull out the key insights. What made first order logic so central? What were the big philosophical and mathematical pushes and pulls that led to it?
Exactly. And I think you'll be surprised at how many twists and turns there are along the way. It wasn't just a straight line from point A to point B.
Okay, so where do we even start with something like this?
Well, I think the natural place to begin is with George Boole. Back in 1847, he published this work called The Mathematical Analysis of Logic, and it was a pretty big deal.
Okay, so Boole, remind me, what was so revolutionary about what he did?
It was kind of a philosophical shift. I mean, before Boole, you had Aristotle and the syllogistic logic tradition, which was mostly about reasoning with words. Boole's big idea was, what if we represent these classes and propositions with symbols, almost like an algebra?
Ah, so he's the one who started turning logic into something more mathematical with equations and such.
Exactly. And what he came up with encompassed what we now call sentential logic, or Boolean logic, as it's often referred to. But here's the fascinating thing. He also had a way of expressing some basic forms of quantification. Like, he could represent all x's are y's with the equation xi equals x.
Interesting. So he was already dabbling in something that looked like quantifiers even back then?
In a way, yes. But we have to be careful not to project our modern understanding onto his work. There are limitations to what he could do. For instance, he couldn't really handle those nested quantifications, like for every city, there exists a road leading out of it kind of statements.
I see. So he had the seeds of the idea, but not the full-blown concept.
Right. And his system couldn't really handle relationships between multiple objects, what we call inary relations, or quantifying over properties themselves. It was very much tied to what we'd call monadic first-order logic. So you can see there's still a long way to go.
And as I was reading in these sources, it sounds like Boole didn't even use dedicated symbols for quantifiers in the way we do today.
That's a really important point. So to call what he was doing full-fledged quantificational logic would be a bit anachronistic. He laid some of the groundwork, but it wasn't quite there yet.
Gotcha. So if Boole is our starting point, what were the next big steps towards what we now know as first-order logic?
Well, there were two major things that needed to happen. First, you needed a way to represent relationships that involve more than just two things, right? Like, not just John loves Mary, but maybe John gave the book to Mary in the library. And then second, you needed a clear and consistent notation for these universal and existential quantifiers, the for all and there exists, that we use all the time now.
And that leads us to Charles S. Peirce, right? I remember that name from some of the reading.
Absolutely. Peirce was very much working in the Boolean tradition, and his work, especially in the 1870s, was a major step forward in handling these kinds of relationships.
Okay, so how did Peirce build upon what Boole had started?
It's kind of interesting. In one of his papers from 1870, Description of a Notation for the Logic of Relatives, he specifically tackled an issue that had been pointed out by Augustus de Morgan, who was another logician at the time. De Morgan had noticed that traditional Aristotelian logic really struggled with inferences that involved relations.
Like what? Give me an example.
Well, imagine you have a statement like, every dog chases some cat.
Mm.
Right. Now, from that, you'd naturally think you could conclude every tail of a dog chases some tail of a cat. But traditional logic had no good way to express this. De Morgan realized you needed a logic of relations, but his own notation for it was really clunky.
Ah, I see. So Peirce came along and tried to streamline that.
Yeah, he recognized that this is a big gap in the system, and he was really ambitious. Like, in his own words, he wanted to extend Boole's logic to cover what he called the whole realm of formal logic, moving beyond just the logic of single terms.
Wow. So he was already thinking big picture, huh?
Absolutely. And he really dug deep into how these relations could be combined, both with each other and with classes, even drawing connections to the kinds of algebraic systems his father, who was a mathematician, had worked on.
Fascinating. But if even De Morgan's system was too complex, how did Peirce manage to make it more workable?
Well, to be honest, his 1870 system was still pretty cumbersome. You can see how the need for a solid theory of quantification with good notation was becoming more and more pressing. But then, in a couple of really groundbreaking papers in the 1880s, Peirce made another huge contribution.
I think I remember reading about this. He was the one who actually introduced the term quantifier, right?
You got it. In his 1885 paper on the algebra of logic, he brought in those symbols we use today, the pi for universal and the sigma for existential quantification. And that was a game changer for logical notation.
It's amazing to think how much we still rely on those little symbols today.
I know, right?
I,
And what's really insightful is how Peirce thought about these quantifiers philosophically. He saw them as kinds of generalizations of the Boolean connectives like and or.
okay, I'm not sure I follow that. How can a for all be like an and?
So think of it this way. The universal quantifier is like saying this thing has this property and that thing has this property and that other thing,
Mm.
on and on for every single individual. So it's like an and. That could potentially go on forever if you had infinitely many things.
Yeah. So it's kind of capturing this idea of a statement being true for absolutely everything in the domain.
Exactly. And the existential quantifier works the same way, but with or. It's like saying either this thing has this property or that thing does or that other thing,
Yeah.
and so on. It's at least one, but it could be many, even infinitely many, if you had an infinitely large domain.
I see. That actually makes a lot of sense.
And this way of thinking about it allowed Peirce to express those tricky nested quantifications we were talking about earlier.
Oh, yeah, like the every city has a road example.
Exactly. Let's say it stands for I loves J. Peirce could then write to express someone loves someone, right? There's at least one lover and at least one beloved, but then pi sigma would mean everyone loves someone. See, that captures the idea that for every individual, there's at least one other individual that they love.
Wow. Those little symbols pack a lot of meaning, huh?
They really do. And that 1885 paper is just jam-packed with important stuff. Like, it also has the first explicit use of two truth values for propositional logic, true and false. And he even outlined a way to determine the truth value of any proposition, what we call a decision procedure. Oh, and he also strongly argued for material implication and showed how you could define negation in terms of it.
Okay, clearly we could spend a whole deep dive just on that one paper. But for our story here about first order logic, what was the next big development from Peirce?
Well, this is where it gets even more interesting, because he goes on to distinguish between what he calls first intentional logic of relations and second intentional logic. And this is super relevant for understanding where first-order logic fits in.
Okay, lay it on me. What's the difference between those two?
So first intentional logic, as Peirce called it, is where your quantifiers only range over the individuals in your domain. It's like saying, for every person in this room, or there's at least one dog on this street, you're not talking about properties or relations themselves.
So that sounds an awful lot like what we now consider first order logic, right?
You nailed it. And he even talks about rules for manipulating these formulas to get them into something called pre-next normal form. That basically means putting all your quantifiers at the beginning of the formula, which makes their structure much clearer. But then, with second intentional logic, Peirce allows you to quantify over predicates and relations as well. Like, you could say, there exists a property such that.
Ah, so now you're not just talking about specific things, you're talking about types of things or even ways things can be.
Precisely. And Peirce uses this second-order framework to define identity in a way that's still used today. He says two objects are identical if and only if they have all the same properties. So if you can find even one property where they differ, boom, they're not identical.
That's pretty deep stuff.
It really is. And it has all sorts of philosophical implications for how we think about sameness and difference. Anyway, the point is that Peirce was way ahead of his time in making these distinctions between propositional logic, first-order logic, and second-order logic. He had a clear understanding of their different expressive powers and how they related to each other. In fact, it wasn't until Hilbert's lectures, decades later, that you see this kind of clarity again.
So Peirce laid out these distinctions, but was he the one who ultimately put first order logic on the map, so to speak?
Well, not exactly. While his work is foundational, it seems to have been largely overlooked during his lifetime. And that's partly because he had a very different philosophical outlook compared to some of the other key players we'll talk about. Like, Peirce was more of a pragmatist and embraced a kind of logical pluralism, meaning he thought different logics might be appropriate for different situations. So he wasn't necessarily advocating for first-order logic as the one true logic.
Right. It seems like a lot of this story is about Not just figuring out the technical details of these systems, but also grappling with these big picture philosophical questions about what logic is and what it's for.
Absolutely.
Mm.
And to really understand why first-order logic eventually took center stage, we have to look at the motivations and concerns of the people who were developing these systems.
Okay, so if Pierce wasn't the one who championed first order logic, who was? Where do we go next in this journey?
Well, while Pierce was doing his thing mostly in the U.S., over in Germany, you had Gottlob Frege. And he was kind of launching a logical revolution of his own, but from a totally different angle.
Okay, so tell me about Freed. What was he up to?
So Frege wasn't so much influenced by the Boolean tradition. He was really interested in the foundations of mathematics, especially the logical underpinnings of calculus and real analysis. All that stuff with limits and infinitesimals that was giving mathematicians headaches at the time.
Right, I remember some of those debates from our deep dive on the history of calculus.
Exactly. And Frege's big philosophical project was to show that all of arithmetic, the stuff we learn in elementary school, could actually be derived from pure logic. This became known as logicism.
Wow, so he was trying to demonstrate that math, at its core, is just a special kind of logic.
Precisely. And that ambition really shaped his approach to logic. Like instead of the traditional terms subject and predicate, he used argument and function, which are more mathematical concepts.
Okay, I see. So he's coming at this from a more mathematical perspective than Pierce was.
Yeah, and his goal was to develop a system of logic that was super rigorous and precise, something that could avoid the ambiguities of natural language and really capture the essence of mathematical reasoning. And to do that, he needed to be able to express relationships between multiple objects and quantify over them.
So he was also on the path towards a more powerful kind of logic, like Pierce.
Absolutely. And what's incredible is that in his book, Begriffsschrift from 1879, he introduces both relations and quantifiers all at once. And he did this completely independently of Peirce.
Wow, so they were both developing these sophisticated logical systems at the same time, but without even knowing about each other's work.
It's one of those amazing cases of simultaneous discovery that happens sometimes in science and mathematics.
Hmm.
And Frege's system was incredibly powerful. Like he allowed for quantification over both individual variables and functions, which was essential for his logicist project.
What do you mean by quantification over functions?
So it's like saying there exists a function such that, or for all functions, it's the case that you're not just talking about specific numbers or objects, you're talking about entire mathematical operations. And this lets you express some really complex mathematical concepts.
So he's really taking things to another level of abstraction here.
He is, and he uses this higher order quantification to define things like identity, cardinal numbers, and mathematical induction, all within a purely logical framework. He also recognized, like Peirce, that there's a hierarchy of logical levels.
Okay, so both Pierce and Frege had this idea of different levels of logic, but did they see eye to eye on it?
Well, that's where a crucial difference emerges. Peirce, remember, was more of a pluralist. He thought different logics might be appropriate for different situations. But Frege saw logic as inherently higher order. Like, for him, the ability to quantify over concepts and functions was part and parcel of what logic is. He wasn't interested in separating out a smaller first-order fragment of logic. It was all one big interconnected system for him.
That's interesting. So they were both developing these powerful logical systems, but their philosophical motivations and what they thought logic should be were quite different.
Exactly. And this difference in perspective is really important for understanding why first-order logic didn't immediately become the dominant system. It took a confluence of factors, both technical and philosophical, to push it to the forefront.
Okay, so you've got Pierce and Frege working on these sophisticated systems, each with their own strengths and weaknesses. But where do we go from there? Who else enters the picture?
Well, after Frege and Peirce, there was Ernst Schroeder, who wrote this massive 3-volume work in the 1890s called Vorlesungen über die Algebra der Logik. It was essentially an attempt to systematize everything that Boole and Peirce had done, bringing it all together into a coherent framework.
So he was kind of like the synthesizer, trying to make sense of all these different ideas floating around.
Yeah, exactly. And you do see Peirce's quantifiers show up in Schroeder's work. But the distinction between first and second order quantification isn't as sharply drawn as it was with Peirce.
It seems like that distinction was still a bit fuzzy for a lot of people at this point.
It was. And Frege himself actually criticized Schroeder's notation because it didn't clearly separate the concept of set membership from the subset relation. That could lead to confusion about whether you were quantifying over individuals or over sets.
Ah, so even the notation itself could obscure some of these important philosophical distinctions.
Precisely. And then there's Giuseppe Piano, who, in 1889, introduced his own notation for universal quantification. But his approach was a bit different. He linked quantification to implication, which, notationally speaking, wasn't quite as elegant as Peirce's symbols.
So a bit of a step back in terms of notation, but he was still contributing to the development of this quantificational logic.
Absolutely. And while Piano didn't explicitly distinguish between first and second order quantification, he did introduce several new symbols that became really influential later on. Like, he was the one who gave us the exist symbol for existential quantification.
That's another one of those symbols we use all the time without even thinking about it.
I know. It's remarkable how much of our modern logical notation we owe to these pioneers. And speaking of influential notation, that brings us to Bertrand Russell and Alfred North Whitehead.
Ah, yes. Principia Mathematica, the granddaddy of them all.
That's the one. Now, Russell and Whitehead's work was a massive philosophical undertaking. They were trying to demonstrate that all of mathematics could be derived from logic, just like Frege. But they ran into a snag, you see.
I'm guessing you're talking about Russell's paradox.
You got it. That darn set of all sets that don't contain themselves, it threw a wrench into the whole logicist project because it showed that naive set theory led to contradictions.
Right, I remember that from our deep dive on paradoxes. It's a real head-scratcher.
It is. And to resolve this, Russell came up with his theory of types. It was a really complex system that basically stratified the universe into different levels or types to prevent these self-referential paradoxes from cropping up.
Okay, so they were dealing with some really thorny foundational issues here. But how does this relate to the emergence of first-order logic?
Well, here's the key thing. Even though Russell and Whitehead had notation for quantifiers, and they were very careful about distinguishing between quantification over different types, they still didn't really have a concept of first-order logic as a distinct system in its own right.
Why not? They had all the pieces, didn't they?
They did, but their focus was different. Their main goal was to show that all of mathematics could be reduced to logic. And for them, logic meant this whole elaborate theory of types, not just a small part of it.
So they weren't looking to isolate first-order logic and study it in isolation.
Exactly. And there's another crucial difference. They saw their system as an interpreted system, like it was about expressing actual logical truths about the world, not just manipulating symbols according to formal rules.
Ah, so it wasn't a purely formal system in the modern sense, where the symbols don't necessarily have to refer to anything specific.
Precisely. And this means that questions about the formal properties of the system, like whether it's complete or consistent, weren't really on their radar. So the unique characteristics of first-order logic as a formal system weren't being investigated yet.
Okay, so we've made it through Peirce, Frege, Schroeder, Peano, and even Russell and Whitehead. But we're still not quite at the point where first-order logic emerges as the dominant framework. So who finally pushes us over that threshold?
Well, before we get there, there's one more crucial figure we need to talk about, and that's Leopold Lowenheim. In 1915, he proved this remarkable theorem that has huge implications for our understanding of first-order logic.
Okay, tell me about Lowenheim's theorem. What's so special about it?
So Lowenheim was working within the Peirce-Schroeder tradition, and he was interested in what we now call first-order formulas. These are formulas where your quantifiers only range over individuals, not over properties or relations.
Right, so basically what Peirce had called first intentional logic of relations.
Exactly. And what Lowenheim showed was that if you have one of these formulas, and it's satisfiable, meaning there's at least one way to interpret the symbols so that the formula is true, then it's also satisfiable in a domain that's countable.
Countable, what does that mean?
It means you can put all the objects in the domain into a one-to-one correspondence with the natural numbers. So like the set of all integers is countable, even though it goes on forever in both directions.
Ah, so it's basically a way of talking about smaller infinities.
Right. And this is a pretty mind-blowing result because it means that even as your first-order formula seems to be talking about a really big infinity, you can always find a model for it where the domain is smaller. This is now known as the downward Lowenheim-Skolem theorem, and it's one of the cornerstones of model theory, which is the branch of logic that studies how formal systems relate to their possible interpretations.
Okay, so this is a pretty deep result about the limitations of first-order logic. But did Lowenheim himself recognize its importance?
Well, that's the thing. He, like many of his predecessors, didn't explicitly identify first-order logic as a special or privileged system. And he wasn't really working with the modern distinction between object language and meta language. So while he proved this groundbreaking theorem, its significance wasn't fully appreciated at the time. It actually took Thoralf Skolem, who we'll talk about in a bit, to really bring it to light.
It seems like there's a recurring theme here. People are developing these powerful tools and proving these deep results, but they're not always fully aware of the implications yet. It takes a while for the bigger picture to come into focus.
It's true. It's like they're putting together pieces of a puzzle without necessarily knowing what the final image is going to look like. And sometimes it takes a fresh perspective to see the whole picture.
All right, so we're getting close to the emergence of first-order logic as a distinct and central system. But who finally makes that happen? Who connects all these dots?
That honor goes to David Hilbert and his collaborator, Paul Bernays. Their lectures in Göttingen during the winter of 1917 and 1918 are widely seen as the birth of modern mathematical logic as a distinct discipline.
Okay, so Hilbert, what did he do that was so revolutionary?
Well, a lot of things.
Yeah.
But for our story, the key innovation was his introduction of metamathematics.
Metamathematics. I'm not familiar with that term.
It's basically the study of mathematics using mathematical methods. So instead of just doing math, you're stepping back and analyzing the systems you're using, asking questions like, is this system consistent? Or can we decide whether any given statement in this system is true or false?
So it's like you're turning the lens of mathematics onto mathematics itself.
Exactly. And Hilbert was a huge advocate for this approach. He wanted to put mathematics on absolutely rigorous foundations. And he saw metamathematics as the key to doing that.
And how does this tie into first-order logic?
Well, as part of his metamathematical program, Hilbert emphasized the importance of having a clear distinction between the object language, which is the language of the mathematical system you're studying, and the meta language, which is the language you're using to talk about that system. This might seem like a subtle point, but it was crucial for making progress in metamathematics.
Okay, so you're saying that before Hilbert, people weren't always careful about separating the system from the way they're talking about the system.
Right, and that could lead to all sorts of confusion and paradoxes, as we saw with Russell's paradox. Anyway, in his Göttingen lectures, Hilbert laid out a series of formal logical systems, starting with propositional logic, then monadic logic, and culminating in what he called the function calculus.
And that function calculus was essentially first-order logic as we know it today.
You got it.
Yep.
It was axiomatized, it was clearly distinguished from other logical systems, and Hilbert explicitly posed those metamathematical questions about it.
So he was not only laying out the system, he was saying, hey, we need to investigate the properties of this system itself.
Exactly. He saw first-order logic not just as a tool for doing mathematics, but as a mathematical object in its own right, worthy of study.
Interesting. But was Hilbert a champion of first-order logic? Did he think it was the ultimate foundation for mathematics?
Well, not quite. He actually still favored higher-order logic and type theory. He saw first-order logic as a stepping stone towards those more powerful systems.
So even though he was the one who really put first-order logic on the map, he wasn't necessarily advocating for it as the be-all and end-all.
Right. But what he did do was create the framework for studying it rigorously. And his collaborator, Paul Bernays, took up that challenge. In his 1918 habilitation thesis, he did a deep dive into propositional logic, which is a simpler system than first-order logic, but it was still a major accomplishment. He proved that propositional logic is complete, which means that every statement that's true in all possible models can be formally proven within the system.
Wow, that's a pretty big deal, right?
Huge. And he also investigated questions like, is this system consistent? Meaning it doesn't lead to contradictions, and is it decidable? Meaning, is there a way to determine whether any given statement is true or false in a mechanical way?
So thanks to Hilbert and Bernays, first-order logic is now officially a subject of serious mathematical study.
Exactly. They laid the groundwork for everything that came after.
Okay, so now that we've got first-order logic firmly established as a system worthy of study, let's go back to that Lowenheim fellow. What happens to his theorem in this new context?
That's where Thoralf Skolem comes in. He was familiar with Lowenheim's work, and he realized that it had some really paradoxical implications for set theory.
Okay, remind me, what was Lowenheim's theorem all about again?
It basically said that if you have a first-order formula that's satisfiable, it's also satisfiable in a countable domain, even if the formula seems to be talking about uncountably many things.
Right. And why was that a problem for set theory?
Well, set theory is supposed to be about sets of all different sizes. including uncountably infinite sets. But if Lowenheim's theorem is true, then even if you write down a set of axioms in first-order logic that seems to describe uncountable sets, you can always find a model for those axioms where the domain is only countable.
Wait, so you're saying there's a potential mismatch between what our set theory is trying to say and what first-order logic can actually express?
That's the gist of it. And this became known as Skolom's paradox.
Okay, I can see why that would be considered paradoxical. So how did Skolem deal with this?
He went back and carefully analyzed Zermelo's set theory, which was one of the first axiomatic set theories. And he proposed identifying what he called definite propositions with formulas of first-order logic.
So he was suggesting that maybe we should restrict ourselves to first-order logic when we're talking about sets.
Kind of, yeah. But he didn't explicitly argue for it as a philosophical principle. He was more focused on the technical implications for set theory.
Okay, so Skolem wasn't necessarily a champion for first-order logic, but he was definitely raising some important questions about its relationship to set theory.
Absolutely. And it's important to remember that this was all happening during a time of great upheaval in the foundations of mathematics. There was this foundational crisis called the Grundlagen crisis, where people were really questioning what mathematics was all about and whether it was even possible to have a truly consistent and complete foundation for it.
Right, I remember learning about that in our deep dive on the philosophy of mathematics. It was a time of intense debate and uncertainty.
It was. And one of the big trends during this period was constructivism.
Constructivism. Remind me what that's all about.
It's basically a philosophical stance that says we should only accept mathematical objects and methods of proof that are constructive, meaning they involve actually building or exhibiting the object or proof in some way.
So it's a more hands-on approach to mathematics as opposed to just abstractly proving things exist without necessarily showing how to construct them.
Exactly. And constructivists were generally suspicious of anything that involved quantification over infinite sets because those are hard to grasp in a constructive way.
I can see how that would be a problem.
It was.
Right.
And both Skolem and another influential mathematician, Hermann Weyl, had constructivist leanings. They were both concerned about the potential for paradoxes and contradictions if you allow yourself to quantify over all sorts of weird and wonderful infinite sets.
Okay, so this constructivist philosophy was pushing people towards more restricted logical systems, perhaps even something like first-order logic.
In a way, yes, but it's not like everyone suddenly jumped on the first-order bandwagon. Even Hilbert, despite his emphasis on metamathematics, still favored higher-order systems. And there was still a lot of confusion and debate about some fundamental concepts. Like, people weren't always clear on the difference between an axiom schema and a second-order axiom, or the different ways in which a logical system could be considered complete.
It sounds like it was a really messy and exciting time to be working in logic.
It was. It was like the Wild West of logic, where all these new ideas and possibilities were being explored, but there was no clear consensus on what the right way forward was.
Okay, so we've got all these pieces in play. The development of formal systems, the emergence of metamathematics, the foundational crisis, and the rise of constructivism. What finally tips the scales in favor of first-order logic?
Well, I think it was a combination of things. The philosophical arguments for restricting quantification to individuals, the realization that first-order set theory was sufficient for most practical purposes, and a growing tendency to distinguish between logic as a neutral framework and set theory as a specific mathematical theory.
Okay, unpack that for me a bit. What do you mean by a neutral framework?
So logic is supposed to be the foundation upon which all other mathematical theories are built. It's supposed to be the most general and fundamental system. But if you allow higher order quantification, you're essentially smuggling in a lot of set theory into your logic because you're quantifying over things like properties and relations, which are essentially sets.
So it muddies the waters between logic and set theory.
Exactly. And some logicians, like W.V. O'Krine, started to argue that higher order logic was basically just set theory in sheep's clothing. They thought it was better to keep those two things separate, have a clean, first-order logic as your foundation, and then develop set theory on top of that.
Ah, so there was a philosophical push for a cleaner separation of concerns.
Right, and this was reinforced by the fact that first-order formulations of set theory turned out to be surprisingly powerful. Like, you could still formalize most of standard mathematics within a first-order system.
So first-order logic was striking a nice balance between expressive power and philosophical simplicity.
Exactly. And then there were the technical results. Remember how Bernays had proven completeness for propositional logic? Well, in 1929, a young Kurt Gödel proved that first-order logic was also complete.
Wow, so that was a major breakthrough.
It was huge. And then a couple of years later, he dropped his incompleteness theorems, which showed that any sufficiently powerful formal system, like first-order arithmetic, would always have statements that are true but unprovable within the system.
So those were pretty earth-shattering results, huh?
They shook the foundations of mathematics to their core. And one of the things they highlighted was the difference between first-order and higher-order logic.
How so?
Well, it turned out that higher-order logic is not complete. So there are true statements in higher-order systems that you can't actually prove within the system. And that was a bit of a philosophical blow to those who saw higher-order logic as the ultimate foundation for mathematics.
I see. So first-order logic was starting to look more and more appealing, both philosophically and technically.
Precisely. And by the end of the 1930s, you see this shift where most logicians are now working primarily within a first-order framework. It becomes the standard for formalizing mathematical theories.
Okay, so after decades of development, all these different strands finally come together, and first-order logic emerges as the dominant paradigm. It's a pretty amazing story when you think about all the twists and turns it took to get there.
It really is, and it shows how these seemingly abstract, philosophical, and technical developments can have profound implications for how we understand the very nature of mathematics and reasoning itself.
Right. And it all started with George Boole trying to turn logic into algebra. Who knew it would lead to all this?
It's a testament to the power of human curiosity and the interconnectedness of ideas.
Absolutely. So I think we've done